Okay, there's a questions number 3B, which I already showed on screen right there. Okay, so part A, I think everyone should be able to get that, yeah? Because you just check for the volume, okay, that given the initial capacity of 2 liter at 20 degrees Celsius. All right, and then there is some sort of like a turpentine, like an oil or something, and then slowly warm it to 80. All right, so you just calculate the change in the volume, you can think of it that way, of the turpentine for both aluminum and the turpentine. Okay, so part B, if the cylinder is then cooled back, how far below? So you just use the original volume, okay, and the leftover of the volume. I mean, you take the volume from the 80 degrees Celsius as a starting point, and then you go backward. You calculate what is going on when you cool it down from 80 down to 20. So you will see that the aluminum is gonna contract more, or actually contract less. And then the turpentine will contract more. So that's why the volume is not gonna fill the whole space that the aluminum cylinders has. So I think that should work out really fine. Okay, so let me sort of draw on screen right here. So let's start from, for part B, you from 80 degree Celsius. That's where your starting point is, okay? And what you can do is think of it like you have, this is your aluminum space. You can think of it that way. And then, oops, sorry, wrong one. And then you have sort of like something built in there. That is the volume of the turpentine in there as well. So I'm using the orange for that. Okay, and then what I'm going to do is I'm going to cool this thing down to 20 degrees Celsius. Okay, so that means the new volume for the aluminum. So aluminum, I use the blue, and the turpentine, then let me use the purple. Okay, so when you cool it down, then the aluminum will shrink. Maybe let me exaggerate a little bit. So it might just go like this. Okay, to a new volume. Along with the turpentine itself, it's also going to shrink as well. That's the question is about. Okay, make sense, huh? All right, so all you need to calculate is just, of course, for the aluminum, eventually you're going to get back to the 2 liter because that's your initial volume. Yeah, okay, so that means this one is definitely is going to be 2 liter because that's was your starting point before, okay? However, for the turpentine, you have to recalculate it because some has already overflowed. Right? So that you have some already overflowed out. So whatever you have left over, that will be the leftover from whatever you're starting from, because you already calculated that the overflow from the part A is that much, 99.4, but you are starting at 2 liter. 2 liter is, you can think of it as like a 2,000 cubic centimeter. All right. So that means your starting volume for the turpentine is going to be this much, 2,000, subtract out that overflow. That's come into here. Oh, sorry. That's come into there already. That's in there. Okay, does that make sense to you guys? Okay, all right. And then you use this to calculate what is happening at 20 degrees Celsius. That's what you have to calculate backward. Okay, so that means, so let me use the volume, okay, or the change of the volume of the turpentine. I use subscript T for that. All right, it's going to be the initial volume, which is right now, is going to be this volume right here. Okay, multiply by the beta for the turpentine, and then multiply by the negative 60, because you want to bring it back from 80 down to 20. So that will be the reduction in the volume. Okay, very good. Alrighty. And from that, actually, you can use this value to be, let me highlight the green here. See, that's the missing volume. Not the missing, that's the decrease in the volume, because that's a reduction in the volume after cooling it down. Okay, so that will be the space that fills the green volume there. And then from that, you can calculate what should be the height that's received from the original, I mean, from 80 degrees Celsius. Okay, this one looks quite complicated already. All right, but because it's the exercise, so I think you have time to do all the calculations here. However, in the exam, it's not this bad. It's going to be sort of more straightforward than this one. So this one is maybe like, it's like part A. I think that's about the level of the midterm. That's pretty much. Okay, but part B is like, okay, just want to add some complexity to the questions. Like, hey, I want to bring everything back to 20. So the leftover turpentine will recede by how much or something like that. So it's just added complexity into the problems. Okay, but that's the whole idea. It's just figuring out what's the missing volume after cooling it down. And then you can trace back to calculate the reduce in height. Okay. All right, would it be okay? So from that, am I saying your name correct? Seda, yeah? Seda, all right. Okay, should be good. All right, cool. Okay. Okay, feel free to ask any questions, guys. Just freestyle today, pretty much. Or if you want to want me to explain anything or any, you know, concepts or revise anything at all, just let me know. Happy to do.ได้หมดเลยครับ anything. Yeah, you can ask any problems, questions, or you want to discuss. You want me to discuss about any concepts or explain anything, just any part of the lecture, handouts, anything. That's good. The what? Doppler effect. Okay, no problem. ได้เลยได้เลย Okay. Which part? The whole thing? ได้ Okay, so okay, let me bring that. Okay, that was a question about the Doppler effect. All right, for those from the Zoom. So I'll bring back that slide and I'll explain again. Okay, it's good. So that's in, here we go. Alrighty. So let's go back. Here we go. All right, so the Doppler effect, the key concept of this one is we would like to calculate the observed frequency, okay, due to the movement or the motion of either the source itself or maybe the observer that is moving. Okay, so that's the shift or the change in the frequency. Okay, that's the observer will hear, right? And the structure that I tried to build for you guys was just to looking at this structure right here. So the goal is we would like to calculate the observed frequency. That's our main goal. Okay, what will be the frequency that observes? Okay, and of course you have two parties that can move. It's either the observer, so we use subscript O for that. So that observer can have some velocity, or the source might be moving, so it might have its own velocity for the source. So we use subscript S for that. Okay, and definitely, of course, the V without any subscripts, that's the speed of sound in the air or whatever the medium that the sound is traveling. All right, and then the rest of this whole thing is it depends on the direction of the motion of observer and source. So by looking at this one, because we are looking at one-dimensional motion, okay, so you only have 4 cases. Okay, there are only 4 possibilities. So these 4 are either the observer or source moving. I mean, for observer, you can either go left or right, and the source you can either left or right. So when you combine these two, you get 4 combinations. Okay, so my logic of picking the signs for calculating the F sub O, that would be pretty much the whole thing about this Doppler effects calculations. Okay, so let's take a look at the first case. So if the observer is moving toward the source, okay, moving towards. So the way that I would like to analyze this one is I just break this into 2 components. So you look at the observer first, what is going on, and then you turn your attention to the source. Okay, and then you think of it one by one. So let's make it a little bit simpler. Okay? Just break it down into two sides of the thing. So let's start from the observer. Over here, you see that the observer is moving toward the source. Okay, when you're looking at this, you don't have to worry about the source at all. You only care about the observer. Is the observer moving towards or away? That's it. The source can do anything, whatever. You don't have to worry about it. Just looking at the observer in this case, the observer is approaching the source. So the logic is when this observer approaching the source, the frequency is supposed to be higher because you run toward against the sound. That makes sense? Okay, because the sound is coming out in all directions like this, right? So actually you're running against the sound. Okay, so that's why in effect, the observer should hear a higher frequency. Okay, so that's why in this sense, I pick the positive side for that. Because it will make the velocity of sound getting bigger, you add on top of that sound velocity by that much. Okay, sounds good? All right, and then you turn your attention to the source. Now, once you look at the source, now you can see that the source is going toward the observer. Okay, so when the source going toward the observer, in general, you will hear a higher frequency as well. Okay, because you are sort of like you're running pretty much like toward the observer. However, because the source is down here, is the denominator, when you want the final effects to have a higher frequency, you want the denominator to get smaller. So that's why I pick negative sign in this case. And that's pretty much the whole logic that I try to sort of build for the rest of 3 cases that we are going to face. Okay, sounds reasonable? Okay, try again. Then you can try the second case, like they both running apart, the observer running away, the frequency should be dropping because you're running away from it. So I pick negative sign for that. Okay, same thing with the source, because your source is running away from the observer, so your frequency should be dropping as well. But because the velocity of the source is down in the denominator, so you want the number to be bigger to have the effects of the final frequency to be smaller. Does that sound reasonable? So I pick positive sign in the bottom. All right, and this will build the whole, 4 possible possibilities. That's it. So that will complete the whole thing. Okay, sounds good. All right, so if this is the case, then the rest is you just try to apply to the actual problems or scenario. So all you have to do is just make sure that you assign the correct observer and source. And then just looking at the direction of motion, and then it's pretty much, it's gonna fall into one of the 4. That's it. Okay. Is that sort of wrap up things? Okay. ไม่แน่ใจตอบถูกจุดเปล่า Okay. Alrighty. So if this concept is good, then I think that's fine. But I don't know, any of you love to do like relative velocity or not? Anyone here is like that? If no, then forget about it. Okay, that's okay. Because some students like to think in terms of the relative velocity. When I'm talking about relative velocity means when you go against something, that thing will appear to you to be moving faster, right? When you go against something. Yeah. Or if you go in the same direction as something, that thing will appear to you to move more slowly. So you can use that concept as well over here. So like I said, the observer moving against the sound. Yeah, this first case here, against the sound. So that's why it appears to the observer that the speed of sound is going to grow a little bit bigger. So that's why you pick the positive sign on top. So you can think it, yeah, some of you love to think in terms of relative velocity. And now when you look at the source going to the left, right? But the sound is also traveling in the same direction. Okay, so sort of the final effects for the sound, it seems like the speed of sound is lower because the source is traveling in the same direction. So in that case, you pick the negative sign in the bottom, something like this. So it depends on what kind of perspective you want to sort of, you know, wrap your heads around this one. But the final form of the equation will look exactly the same. Okay, yeah, okay. But from the experience, seems like just think of what happens to the observed frequency seem to be more natural. Okay, I think. อันนี้จานเดาเอง Okay, very good. So this one is definitely will be in the exam. So that's a good question. แล้วก็ไม่ยากด้วยนะครับไม่ต้องกังวลนะครับไม่ซับซ้อนเลยเฮ้ยที่สำคัญต้องอย่าคิดว่าข้อสอบยากก่อนนะข้อสอบมันไม่ยากก่อนเราจะรู้สึกดีขึ้นถ้าคิดว่าข้อสอบมันจะมาแบบโหต้องยากแน่เลยหรือแบบมันต้องอะไรเงี้ยมันจะทำให้เราแบบนี่ว่ามันจะจิตตกนิดหน่อยแล้วมันจะทำให้เหมือนกับ efficiency เรา drop ไปหน่อยใจไม่ค่อยดีอะไรเงี้ยมันไม่ยากต้องคิดว่ามันไม่ยากจริงไม่ยากครับตารางอะไรเอ่ยโอ้ไม่ต้องเลยทุกอย่าง given หมดถ้าสำหรับอันไหนเขาจะบอกว่า C for this one equal to what อะไรเงี้ย so there's no memorization required at all don't worry about it yeah and for the formulas you already seen that yeah the formula sheet in the front so in terms of the numerical values don't have to memorize แล้วเอาเข้าจริงถ้ามันออกมาแล้วมันต้องมีค่าคงที่บางอย่างแล้วไม่รู้จริงก็ติดคามันไว้งั้นเลยก็ได้ ไม่คอนเซิร์นเลยครับตรงนั้นสบายมากได้ครับโอเค alright so เอาตัวอย่างนั้นอีกรอบใช่ไหมที่เราคุยในห้องใช่ไหมโอเคได้ครับไอ้ตรงที่เป็นซอส2 source อย่างนี้ป่ะโอเคได้ครับโอเค alright so there's a question about the interference which is the last topic here okay so the concept of interference is just a simple summation of the waves. That's it. Okay, because the underlying principle is we call the superposition. So it's like 1 + 1 = 2, 1 - 1 = 0. So that's the nice thing about this one. It's just algebraic sum of the waves. Okay, so that's a fundamental of interference of waves. And because we are focusing on the sinusoidal wave, so it's sort of like periodic waves. Okay, so you know its frequencies. So no matter what the wave is, all you need to do is just sum the two together. But when it's sinusoidal, the nice thing is you will repeat the form of the wave every time you go one full cycle every time. Okay, so whenever you wait for one period, or whenever you slide yourself by one wavelength, you get the form of the wave look exactly the same, just like you already saw it one period or one wavelength before. Okay, so everything is periodic. Everything come back to the original form, just like before. So we use that idea to talk about when you have interference, it means you have two waves coming in at one spot. Okay, and then you want to know how, I mean, for algebra, you just add them. But because we are looking at periodic waves, so there is a two extreme cases that we can consider. The first extreme is when the two waves look exactly the same at the spot of interference. So we call that in phase. So that's the top case right there. When you say in phase, mean the movement or the rhythm of the two waves is in sync exactly, up and down in the same rhythm like this. We call them in phase. All right. So when they are in phase, it means, of course, the displacement is always in the same direction. So that's why the final effects is you get the amplitude to be twice as big. Okay, so that's why you get the constructive interference. So the final waves will look bigger, twice as big, if the two waves are exactly the same. On the other hand, the other extreme is when the two waves are exactly opposite all the time. Okay, so one has a positive displacement, the other one is go negative displacement. So in this case, in terms of the phase mean that change or that difference in the angle behind the side. Oops, sorry. Okay, the interference, the phase difference, that is the angle behind the sign. Okay, will tell you what's the difference between the two waves. And whenever you want this to be perfectly opposite like this, that means you have to slide the wave by half the cycle. Okay, but when you say half the cycle, you can speak in terms of the angle, which is the phi, the phase. Half the cycle is 1 pi. Yeah, that's half the cycle. Or if you want to speak in terms of the distance, that will be half the wavelength. If you want to speak in terms of time, that will be half the period. Yeah, make sense? Yeah, so that's why every time we talk about waves, you can speak in terms of the distance. So you use like the lambda, the wavelength, that one full cycle. You can speak in terms of time. So that would be one period that you have to wait until everything come back to the original form. Or if you want to talk in terms of the angle, or in physics, we call it phase. Yeah, phase, that will be 2 pi, that will be one cycle, right? So you have pretty much three ways to talk about the position of the waves. Okay, either this distance, okay, lambda, time, that's period, angle or phase, that will be your 2 pi per cycle. Okay, so that case, when you want them to be perfectly opposite, that's when the phase is difference by pi. That's half the cycle. Okay, however, you can always top up with extra cycle all the time, correct? So that means if you're starting from, okay, let's start from the top case. So if you have no difference at all, so the phi, the phase difference will be 0. So that's guaranteed the two waves will look exactly the same. That's cool. Okay, but you can top up with extra cycle. The wave will come back and look exactly the same. So that's why you can add 2 pi. That's okay. Or you can add extra 2 pi to it. You can get 4 pi, 6 pi, on and on. So that means every time that the phase difference are multiple, an even multiple of pi, 0, 2, 4, 6, 8, on and on, you get constructive interference. Okay, but now I can speak in terms of wavelength if I want. So if I want to speak in terms of the wavelength, it will look like 0, lambda, 2 lambda, 3 lambda. Correct with me? So if you talk about distance, if the distance difference is multiple of lambda, you get constructive interference. Yeah, okay, huh? All right. And then we use the same thinking for the destructive interference. So we already said the first case that's possible is 1 pi, half the cycle. You can top up with extra cycle. You can add 2 pi to it. So you get 3 pi, 5 pi, 7 pi, on and on. So if you hit this phase difference of odd multiple of pi, you get perfect cancellation because they are always opposites. And then we can speak of this one in terms of the distance. So that will equivalent to half the lambda. And then I can add on top of it for extra lambda, it will be 3 lambda and a half, 5 lambda and a half. Okay, sounds good? All right, so every time you are have you having the path difference or the distance difference of half the cycle, half the wavelength, or maybe 3.5 of the wavelength, 5.5, you get perfect destructive interference. Okay, all right, sounds good. So that's it. So that's why from these two, I can sort of give you the conclusion here, down here. That's what we discussed in the lecture. So in terms of the distance, that's in practice, in practical applications, that's what you usually do, because you measure the distance. You don't measure the phase. That's kind of hard to do. Okay, so if you measure the path difference or the distance difference, and if it's multiple of wavelength, which is the top case right here, that's nice, multiple of wavelength, then you get a constructive interference. Okay, good. All right. Or if the path difference is sort of odd multiple of λ.5, okay, you get destructive interference. That's it. That's pretty much conclude the interference of waves. พอได้ไหมเหมือนว่า get idea นะ okay, kind of cool. All right. Okay, so in problems, usually what you're going to face is going to look like this. Yeah, most of the time you have two sources that generate waves coming out. All right, so actually if you're already in this room, this is kind of nice. If you look at in the front, you have two speakers. That's exactly what the condition of this one is. Okay, so you are standing at your position. All you need to do is just you measure the distance from you to the first speaker, and then you measure your distance from you to the second speaker. Okay, then you get the R1 and R2 in this problem. Okay, and then in reality, all you need to do is just check the path difference. So what is the distance that difference between R1 and R2? Okay, and then you just check the condition of that difference. If it's perfect multiple of lambda, at your sitting, you'll hear a loud noise because the sound from two speakers will interfere constructively. Okay. But if your R1 and R2 difference turns out to be odd multiple of λ/2, at your sitting, you hear nothing. I mean, in perfect world, it will be perfectly quiet. Okay, but in reality, it's not. But you're gonna hear a lower sound. Okay, sounds good. All right, so that's sum up the whole idea of something that we can do here. All right, so the key is figuring out figuring out this. That's a key. Path difference. You measure the distance from you to the first source and from you to the second source and take the difference. Okay, and the reason we put in the absolute sign because we don't care much about positive or negative. We just care about the difference. So we just take the absolute sign in there. And then once you get that number, you just check, is it a multiple of lambda or not? If it is, that's constructive interference. Is it odd multiple of λ/2? If it is, then that's destructive interference. If it's none of the above, so it doesn't fit any one of the two cases here, it's just somewhere in intermediate. You're just going to see some, it's the addition of the two waves, but it's not going to be the extreme. Okay. Somewhere. So that sounds good. Okay. พอได้ไหมนะ Wow. Yeah, actually, because in this meeting room, we have too many speakers. But in reality, if it's a lecture room, we can test this. I can generate like some frequency from the app and then just send it out. And then you move your head a little bit. It will, the level of the sound will fluctuate a bit. There'll be some point that is a little bit louder, and then it's going to get a little bit quieter, and then it's loud again when you just sort of move your heads around. But I don't think it will work in this room because 4 speakers, that will interference effects will, with some reflection and all the stuff as well. A little bit crazy there. Okay, but that's pretty much the idea. Okay, nice. Actually, while we're speaking about this, oh, that's a good point. Okay, that's a good question. I have some extra things to tell you. This, oh, well, this is after the fact that I have already seen the midterm paper. So that's, okay, ถือซะว่าอันนี้ไม่ได้มาบอกข้อสอบนะครับ แต่ว่า I think that's something you should know and I think it's good to know เดี๋ยวอาจารย์ขอคิดแป๊บนึงนะเดี๋ยวมันจะเหมือนเฉลยบอกข้อสอบมากเกินไปวะโอเค okay, but this topic is nice because it seems like, okay, this is I think the information that I can give it to you. It turns out อาจารย์ธเนศ put 2 of this in the exam, which is bad. I think it's too much, but too late. The paper is already printed. So, all right. So for those of you that's online, that's kind of, all right, check this out. Okay, this is good. I think he kind of forgot. That problem is supposed to be like this topic here, but then I told you like I didn't see this topic in the exam. So I think he kind of forgot and then put 2 of the interference problems in the midterm or something. Okay, all right. So let me add a page and then I'll explain what is going on here. But this will be like telling you the midterm problem somehow. ซึ่งพวกเราคงไม่หมายโดยธรรมชาตินะ Okay, very good. Okay, let me, what do I do? Add a page. Okay. Okay, so it turns out there is, we call it, is the same topics, all right? There's nothing new. It's still the interference of waves, okay? However, there is that additional mathematical approximation that add on top of this, okay? So let's follow me a little bit. So if I have source number 1 and source number 2 over here, okay? And somehow I am quite far away from these 2 sources. So for this problem is like I'm pretty close to the source. Okay, so like the separation between the source is like in this case like 3 meters, but then I'm only like 8 meters away. So it's like everything is just around me. There's no difference. But there is a possibility that the 2 sources maybe some distance apart, but then the position that you want to observe the effect of the interference is quite far away. For example, this is not in scale, but it could be like this separation is D. Yeah, but then you are like here, like you are far away from here, like point P, that far. Okay. So in this case, the logic is going to be quite the same. That the technique is going to be the same. Is I'm just going to have to measure the distance from S1 to P. Correct? Because that's what you want all the time. And eventually you're going to have to measure S2 to P. No difference, still the same techniques. And then I say, all right, if you can figure it out, that will be S1P distance and S2P. And then you can call this like R1 and R2, just like what you had before. No different, okay? And then you can still use R2 minus R1 equal to what cases, and then you can determine which case is going to be the constructive or destructive. However, when the point of observation is so far away, making a measurement of R1 and R2 sometimes is sort of inconvenience. So there is another way that you can do this by approximate. Here we go. So I'm going to show you this. I'm just going to give you like a line of sight here. Let me sort of split this in half. Okay, here we go. All right. And let's say that I know that you are somewhere away from the source by the distance. Let me call L for now. Like you are like L away. Okay. And you know that R1 and R2 is not going to be too far away from the L. It's somewhere around L, R1 and R2. However, I can make some measurement by doing only once. So I will turn my attention to this. So I will look at the angle instead. Here we go. I'm going to do this here. the red line. I don't know, is that easy to see here? Yeah, still fine. All right, so instead of measuring R1 and R2, I will measure the angle. Let me call theta. Okay, so the theta will be the distance. I'm sorry, the theta will be the angle that point P make with the line that cut through or cut the position of the S1 and S2 in half. So sort of like I'm midway between S1 and S2, and I draw a line perpendicular to the D, okay, coming out like that, okay, over there. Okay, very good. So what I can see over here is, it turns out because I cut them in half. So if you look carefully here, okay, I can pretty much try to draw a triangle that look the same on both sides around this. Okay, let me do it nicely here. So I'm gonna cut this perpendicular like this. So if you look at this one in the big picture over here, okay, so the triangle that I have is gonna be like an isosceles triangle, สามเหลี่ยมด้านเท่า. Yeah, so that's mean by looking at this, okay, follow me a bit here. This is like very big sort of image here. So the distance here that I'm highlighting, okay, and another distance here that I'm highlighting green, okay, these two will be exactly the same length. You guys with me? Okay, the yellow highlights and the green highlights will have the same length. So the difference in R1 and R2 will be just this right here. That's the difference. You guys see that? Okay, so all I want for this is just, if I know this length, that will be my R2 minus R1. With me? Sounds good. And I can calculate R2 minus R1, that mini length over there, by looking at this triangle right here. Approximately, see that? Approximately means because that big thing is theta, this tiny thing will be theta as well. Approximately, it's going to be very close. Okay, and that's it. If you look at this triangle over here, the black triangle, this R2 minus R1 that we want is just going to be the sine theta. You guys with me? พอไหวไหมเนี่ย yeah. D sine theta, because okay, if you call this X, this distance is D, the opposite over hypotenuse, that's sine. Okay, sine theta is opposite, which is X over the D, the hypotenuse there. So that means the X is just the D multiplied by the sine theta. So that's it. So that means I can do S1P, okay, I can use R1. R2 minus R1 is going to be about D sine theta. So as you can see now, you don't need to actually measure the R1 and R2. All you have to do is just measure the separation between the two sources, the D, and just using the angle that the point P make with the midline. Okay, and that's it. D sine theta is approximately equal to the path difference. And then you can sort of match this with the condition that you had before. So it's still the same idea, is you just checking the path difference against, is it multiple of lambda or is it odd multiple of lambda over 2? It's still the same trick and techniques. But this is the mathematical approximation that allow you to calculate the path difference, the R2 minus R1, from the separation D and the angle that it makes with the midline in between. Sounds reasonable? อันนี้เหมือนบอกข้อสอบ So that suggests that this kind of question will pop up in the exam somehow. All right. And you're probably wondering like what kind of conditions that you're going to have to use this one. So For the sound, it seems like it's good in this shape already. You just figure out R2 minus R1, R1 minus R2. That's good. But this one seems to come in when you talk about different kind of waves. Usually you do this with the lights. Because every time you do the light, usually like, you know, like your smartphone or that stuff, you have a tiny light source or that stuff, and then you are quite far away from it. So interference will pretty much like, with respect to the position of the source, is quite far away. So this application of approximation here usually will show up in the light waves, okay? And for the sound waves, usually you don't need to do this d sine theta approximation because the dimension is pretty much the same, like 5 meters, 10 meters, so you just do the measurements, okay? But this one is, when you talk about light, is like wavelength is super short, every distance looks so big, then you don't want to do R1, R2 anymore. You just do the angle instead, something like this. Okay, but the concept stays the same. That's constructive. That's destructive. There you go. All right, so actually that's a good question. Reviewing the interference. All right. Very good. Yeah, but I plan to talk about this one no matter what. So you guys have to know this. เดี๋ยวจะหาว่าอาจารย์ไม่บอก เดี๋ยวจะมากดแค้นกันทีหลังนะจ๊ะครับผม okay, that's another good question. It turns out there is one question about entropy, but it's straightforward and simple calculations. So that's why I put entropy questions in the extra problems for you to practice, like 2 questions in there. So that's enough. So I think the key of the entropy that we need is just calculate the heat divided by temperature. That's it. Okay, so if you get the formula there, that should be good. There's no calculus, there's nothing. So the problems that you're going to face is when you have constant temperature all the time. So that's why your problems go back to calculating the heat. And then you divide it by temperature, you get the entropy change. Yes. อันนี้เหมือนบอกข้อสอบไปแล้วครับ Okay, นั่นแหละ that's it. But it's like a mini questions in there. It's not like a big question about entropy. Yeah, it's really like part C or part D of the problems. Okay, good. Okay, very good. So let's okay. There you go. All right, just quick note. Okay, so it seems like the key okay. Okay, so most of the questions will be constant temperature process somehow. คล้ายๆอาจจะประมาณนั้นเลยครับแต่ว่าก็ไม่น่าจะมียูนิตอะไรที่มัน different so much it's gonna be like simple maybe liter I'm not even sure it might be in like cubic centimeter you might have to do it like convert it to cubic meter something like that calorie don't remember but is that in not in the formula sheet no yeah I don't remember but you can ask Ajahn there that's okay yeah so if it's just a conversion factor you can ask that's simple yeah that's allowed บอกอาจารย์ what is the conversion factor I don't remember something like that but if it's just like a prefix and all this stuff then usually Ajahn will not tell you like Ajahn what is like how many millimeter in 1 centimeter something like that I think that's your job to do it but for the conversion factor or some constants if you really want to know like what is the gas constant numbers and I think you can ask in the exam room that should be good yeah which equation นะครับ Carnot equation is it already on there I think oh normal efficiency okay so yeah it's that means you just have to know the condition for the Carnot a little bit and that's easy because it's only let me write it out here so for the Carnot condition for the Carnot engine so the key is just the ratio between the heat is the same as the ratio between the temperature that's it so that's kind of sort of easy to oh you want that one okay so in the formula sheet I think it gives you just the definition of efficiency okay so which is work over Q hot this is what we want right okay let me put absolute sign there okay but then the work is just the difference between the heat that you bring in and your heat that you discard out yes okay like this and then you just do the ratio thing a bit that's it so I think this is in the formula sheet is this one just this efficiency definition yeah then all you need to do is just use this ratio plug it in here that's it so that's a Carnot engine case อะไรครับ reverse heat pump our work going the other way around well I don't think that's if that is the case then it's not too bad I don't recognize there is any heat pump or air conditioner but the idea is just exactly the same I think yeah you mean efficiency right for the heat pump is what you're saying or if you have like a heat pump machine running oh okay so when you talk about the heat pumps or the stuff actually okay let me give you this idea here so usually when you are given a PV diagram yeah okay and you usually will be given a cycle something cycle so it will go like bam 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 something like that's what we did in class go like this yeah so it turns out if your cycle go clockwise that is the heat engine but actually if you reverse that arrow that's your heat pump already that's it because it just do things in the opposite direction so the calculation will look exactly the same but some of the quantity will go reverse right because when you go one way things may be like the change in the U will go decreasing but if you want to go backward it's increasing So it's more like you do calculations just like what you did. You do the work, is the area under the curve. The delta U is just the same formula, 3/2 nRT. And then you can calculate the heat just like before. Okay, but it's just everything go opposite direction. So actually what you're seeing over here, if you reverse the arrow, that's already heat pump. Yeah. So it's still under first law of thermodynamics. So it's quite okay. So I can do this and go reverse. That's a heat pump. There you go. All right. So I don't think you have to worry too much about is it going to be the heat engine or heat pump if the question is asking you to refer to the PV diagram. So that would be like, you just do just like, you don't have to worry about what kind of machine this one is. And then I'll discuss a little bit about the formula that I just talked about today. Okay, maybe there is a little bit more. So I think worth mentioning because Ajahn Thanet put it there. So it might worth talk about it. I'm interference. Yes, yes, yes. So I would like to talk about here. I just noticed that in this formula sheet, there is an extra terms coming here as well. All right. So whatever now in the front seems to be okay. All right. So let's wait a bit and then I'll explain about what's going on here. All right. So that's a good point here. Okay, for about the format of the lecture, we can vote in our live group. แต่อาจารย์คิดว่าก็มัน don't need to come to the I mean here. I think that seems unnecessary. Yeah, doesn't seem to no need anymore. แต่ตอนนั้นเหมือนมีคนบอกว่าอยากมาเรียน on campus อยู่นะมี some นะใช่ไหมมีไหมis that among us here no he has that exam today okay so there might be only single person so it would be bad it's like hey okay let's meet on campus and then there's only one person shows up and everybody else is like yeah I'm at home okay so I have one more comments on this formula okay because okay for those that looking at this one d sine theta I already explained where the d sine theta is from okay and this one you now see that it's just like constructive right this one is constructive and this is a destructive case okay all right now there is an extra terms extra formula toward the end dy over capital D so this one actually it's an additional approximation additional I have to say additional because so let me bring back that slide here okay so over here so let me pull this one down okay here we go so because from this one we already see that you can calculate the path difference that's the PD in the formula sheet path difference approximately equal to d sine theta right but then you can do further approximation by looking at the sine theta right here. So when you look at the sine theta, it's actually is going to be the opposite. Let me call this according to the formula. Let me call that is that y here. There you go. Okay. So the sine theta is going to be opposite, which is y, over hypotenuse, which is that's weird line over here on the light blue here. You can call it like some, well, what? Let me call A, something like that. Okay, so the sine theta is going to be y over a. But then when the angle is quite small, so that means the L, the capital L is so far away. Okay, so when things are so far away, that A is approximately equal to the L. I don't know if that makes sense to you or not, but when you are so far away, okay, you say, hey, with some angle theta, if the theta is not that big, the A and the L are about the same thing. So that's why you can approximate this sine theta to be equal to approximately y over L as well. Okay, now all right, so that's why this formula can be further approximate to be dy over capital L, something like this. So in mathematics, actually the approximation we are doing is when theta is small, sine theta is approximately equal to the tan theta. That's what it is. You can punch the calculator and try. So if you try to find the value for the sine of some angle, and you do the same thing with the tan of that angle, the numbers that you get is about the same when the theta is still small. Okay, so that's why you say, hey, I don't want to measure the hypotenuse, measure the separation from the source toward the screen or toward whatever the wall or whatever is easier. The capital L is so easier to measure. Just take the capital L and say, I'm good. So that's why you can further approximate the sine theta to be just the height from the midpoint divided by the separation from the screen or whatever the wall to the source location. Okay, so I hope this clear up what this formula sheet is about right here. That's what it is. So that, oh, it looks bad. Something like that. Okay, so I hope this one is clear, and it might be even be in the exam. อาจารย์ชักไม่มั่นใจแล้วแต่ไม่กล้าเปิดข้อสอบดูตอนนี้เดี๋ยวไม่เป็นไรไม่เป็นไรอาจารย์เดี๋ยวจะไม่ได้เดี๋ยวพลาด
พวก kinetic กับkinetic กับ potential ไม่ออก
But in mechanics or in oscillations, if it's in oscillation, it should be there. It's still energy, right? Yeah. If it's the oscillations, there is like question about, it could be velocity, kinetic energy, spring energy. I think it should be there. I think it's fine because we have a topic in energy in the oscillations. Yeah. Oh. But like pure kinetic energy calculations, yeah, I mean that shouldn't be just like a pure like Newtonian physics. It shouldn't be there. Okay. Course 5อันนี้ใช่ไหมข้อนี้ใช่ไหม Okay. What's the problem? Okay, so let me try sort of draw the diagram a little bit for this one. So you have an aluminum aluminum, 100 gram. It's a 250 gram of water. ครับแป๊บนึงนะโอเค ที่สงสัยว่าเราจะเอาห้องพิมพ์หรือเปล่าแต่มันเราเมีติ้งดูเหมือนประชุมซีเนียร์กันมาก Okay. All right, sorry guys, just have a question about meeting room here. Okay, so let me draw. You have an aluminum calorimeter, which is, think of it like a container. There's a water in there. Okay, everything start at 10 degrees Celsius. Okay. Now you have two metallic blocks placed into water. One is known to be copper. The other one is something 70 gram and at 100 degrees Celsius. Eventually everything cool down to, sort of final temperature is 20. Okay, what is this? Okay, what's missing information? Probably you're thinking of what is the specific heat of copper? Is that what you're thinking? Oh, okay. Usually if it's in the exam, it will be given. So because this is like an exercise, you can refer back to the table. Yeah. All right, but so let's set things up here. So you have two metallic block. So let me put in like copper. Maybe like this. Okay, so that's copper. This is X. You don't know what it is. Okay. And copper is 50 gram, 80 degrees Celsius. Okay. And another one has 70 gram at 100 degrees Celsius. Here we go. All right. So you dump everything into the water. Everything sort of stabilize at 20 degrees Celsius. That's toward the end. Okay. So you can think of this problem as there will be a portion of the system that is cooling down, and that there will be another portion of the system that warming up. Okay. And eventually all of them will meet at 20 degrees Celsius. Okay. So there will be an exchange of the energy in form of the heat. So the things that get hotter will get cooler because it's remove heat from itself and then throw it into the cooler part of the system, make those parts to be warmer. Okay. All right. So let's take a look at this one. So you can think of this copper to be cooled down from 80 down to 20, correct? Yeah, the copper first. So let's start from the copper. So there will be the mass. Okay, let me put the black one here. The mass of the copper, the C of the copper, which we can look it up, and the delta T of the copper. Okay, starting from that. Same thing with the X material. And that seems to be it. Yeah, these are the two parts of the system that get cooled down from whatever initial temperature down to 20. Okay, so this one will be the one that gives off heat. Okay, and then you have to equate this amount of heat that flow into the cooler part of the system and warm things up. Okay, so that will be the aluminum. So it will be mass of the aluminum, the C of the aluminum, and the delta T of the aluminum. So that's the one that pick up that heat and warm up. Plus the water will warm up as well. That's the whole main equation right here. Okay, so let's try substituting the numbers in here and see how it goes. So what you're gonna get is mass of the copper, which is 50 grams. So let me keep the unit gram in there because they all use grams, so I don't have to convert anything. C of the copper, assume that we can look it up. So that's supposed to be some number, plug it in. Delta T over here. Now, as we said, we usually talk about the temperature change, okay, by not talking about the sign. Okay, I don't know, you sort of recognize this one. Yeah? So you can think of this one as like, I'm talking about just the absolute value of the heat that flow. You know that this portion of the heat will flow out because it's hotter. Okay, eventually it's gonna sort of give off some heat away. All right, but we just calculate the amount of heat. So we put the absolute sign there. So over here, I can say it's going from 80 degree down to 20. Yeah, that's the copper. So the change of the temperature is 60 for the copper. With me? Okay, this one. Okay, plus the second term, the mass of the X material that given to be 70 gram. Okay, now that's the specific heat of X, that's the one that you want to calculate. And the delta T for the X, you coming from 100 down to 20, so the change is 80 degree. Okay, let me put unit in there. Okay, make sense? Okay, all right, and that's it. On the left-hand side, you equate this to the right-hand side. So the mass of the aluminum, 100 gram. C of the aluminum supposed to be given. And the delta T for the aluminum, you starting from 10 degrees Celsius. And then it's warmed up to 20. So the change is only 10 degrees Celsius. Okay, and that's it. And then you finalize with the mass of the water, 250 gram, C of the water, and also 10 degrees Celsius as well. And that's it. The only unknown in this equation is the C sub X. And then you can solve for that. Okay, รียบร้อย And for the barium, I think there must be like a huge table to look at. And then you just pick the one that closest to the C of X that you got from this calculation here. Okay, all right, so that's good. Oh, that's the first equation. That's what it is. Okay, so this is the Q hot. This is the Q cold. Right. Okay. So this is the one that we discussed in class. So if you want to do the negative sign, okay, the delta T over here will be a negative delta T. With me? So if you want to use the negative Q hot equal to positive Q cold, you have to keep the delta as is. As is means the final minus initial. So the left-hand side will be cooling down. So the delta T will be negative. So when it hits with the negative sign in the formula, you get back the positive one anyway. Or you can just get away from all this by just put the absolute sign there and be done with. Yeah. So it depends on your approach. You want to just calculate the amount of heat, or you want to keep the equation just like there's flow in, flow out. If you keep that one, you have to keep the definition of delta as a proper definition of the change. Final point minus initial point all the time. But you end up with the same equation. Yes. Yes. Okay, is it here? Okay. It doesn't show up. Midterm. Here we go. All right. Down there. Okay, so number 3 here, right? Yeah, okay. All right, so there's a question about figuring this out. Okay, so you have a heat engine that operates according to the following cyclic process, okay? The gas used 3 mole monatomic gas, okay, that's what we agreed on. Okay, part A, how many atoms of gas do we have here? Okay, this one is still not thermodynamics. It's just a property of gas. Okay, so that means you can pick information, whatever from the PV diagram that you sort of know specific numbers. Like over here, I can see that point A and point C is already done. So you know the pressure, you know the volume. Okay, so that means you should be able to, wait. Oh, part A is number of atoms. Okay, it's even easier. See, don't overthink about it. Okay. You already given the number of mole. So number of atom is just 3 times Avogadro number. That's it. See, okay. See, I told you, don't overthink about this one. It's like, so it's 3 times 6.02 times 10 to 23rd, something like that. Okay. Is that given in the formula sheet? That fixed number there?
No, they just give you the Avogadro number.
That's given, Avogadro number? Oh, okay, so that's good. So that should be fine. So Avogadro number is there. Okay. What's the number? Ah, okay, 6.022 times 10. Okay, perfect, done. Okay, part B. What is the volume and temperature of the gas at point B? Okay, so when you look at this one, they say be careful with the units because the unit given over here is liter. Now that's the weird one, yeah? Okay, the ATM, which is fine. You have a conversion factor right here. So you can convert from ATM to Pascal, which is no big deal. Okay, so let's take a look. So you can see that now at point B, that's a part that you don't know the numbers yet, right here. That's point B, you don't know the volume. And they want you to figure out the volume. So you can use, up to you now, PAVA over TA equal to PBVB over TB, PZVC over TC, up to you. Okay, because according to the equation of states, this PV over T stays constant at all time. Okay, so you can match point B with any point that you already know the numbers, and that should be good. Yes.
Just use like V equal nRT.
You can do that too. Yeah. So they will be all the same. Doesn't matter. But to me, the reason that I picked this one because from the look of this one, um,
Like you know that temperature point A and point
right, they are
so
at the same temperature between A and B. Okay, so that's why if you compare between A and B, then it's gonna be 5 times as well. Okay, let me write it down. So because you just want to pick the point that is easy to calculate, okay, and you know A and B are connected through isothermal process, so they're sharing the same temperature. So that means what I'm going to do is I'm going to compare between point A and point B. So you can say PAVA is going to be PBVB, okay, because T cancel out, they're sharing the same temperature. So as you can see, at B, the pressure is 1/5 of A. จุด B มันเป็น1 ใน 5 pressure. So the volume has to compensate for that. So the volume has to expand 5 times to make the product between pressure and volume constant. So now I can say right away, this must be 50. Okay. All right, because the product stays the same. Or you can just plug it in. PA is 5 ATM. The volume at A is 10 liter. Pressure at B, that's 1 ATM. And then the V at B, that's 1 you want to figure out. And you know it has to be 50 liter. So that's done. Right.
we just assume where they have like 5 line on the bottom.
Have the what? 5?
Yeah, like it's like
Yeah, but sometimes, you know, maybe it's not drawn in scale on and on. So you don't want to risk sort of rely on just the figures. Yeah, just rely on your calculation. I think it's better. Yeah. Yeah, but this one is just nice PV diagram. So that, yeah, you can count the number of ticks in there if you want. Like 1, 2, 3, 4, 5 is 50. Yeah. But sometimes the figure might not be so nice. Okay, and what is the temperature? Okay, so now you know everything. Okay, so once you know everything, you can figure out the temperature by doing PV equal to nRT. Okay, and that's it. So you can say, you can pick a point now because all the information is already there. You can calculate because right now you are focusing on point P. So B VB equal to nRT at B. Okay, and that's it. This is the only point that you have to be careful with the units. because you want the temperature to be in kelvins. So that means the pressure has to be in Pascal in SI system, and the volume has to be in cubic meter. So I think this is the part that you need unit conversion. Okay, so, okay, let me write it out here. Running out of space a bit. All right, let me do that. Okay, here we go. So let's use that. So what you have here is, now I can say T at B is just PB VB over NR. And now plug in the numbers. The pressure at B is 1 ATM. So I say 1. But then I can convert ATM to Pascal by multiply by that factor there. That in Pascal. Okay. And the volume is going to be 50 liter. So I can turn liter into cubic meter by converting as well. Running out of space here. Okay, so let me move this one out of the way. Somewhere. Okay, all right. Okay, so let me squeeze in there. There you go. Volume is 50 liter. 50. So now it depends on how you want to convert. Usually what do you do? ทำไง from liter to cubic meter ทุกทีเราทำไงเอ่ย ได้ไหมอันนี้ทุกคนทำอย่างนี้ไหม yes 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 ทุกคนโอเคไหม sort of โอเคนะโอเค ได้ถ้าได้ก็เอาตามนั้นเลยโอเค cubic meter okay very good all right now divided by n is given to be 3 moles so that's just 3 and then r now supposed to be in there in your formula sheet 8.31 yeah very good all right and that's it you just punch the calculator there so I'm not sure about space given here you just try to squeeze something in there but in your calculation if you are not putting like units in there I think that's okay คือหมายว่า during your calculations you might not have to like put in all the units for all of the quantities okay you just make sure that you put the right numbers in there I think that should be enough and then you just summarize the final units at the end but in this particular problems it's sort of like it's forced you to use kelvins anyway so you just calculate the numbers and put the numbers in there should be good all right but seems like space is not enough somehow okay part C calculate the work done from A to B all right here we go from A to B okay so the nice thing about this one is it's isothermal process yeah so we all know that the work done is going to be area under the curve for sure so that's going to be area under the curve whole thing here okay however we have done this in the lecture already and I think it's already in the formula sheet I'm pretty sure so let's check yep yeah just search for it a little bit search for it a little bit here we go there you go yeah it's there all right very good so W isothermal is nRT log V final over V initial and that's it so this part of the problem seems like plug in the known values the only unknown value it seems to me at this point is it's all known actually there's no unknown okay so that's it so I say W isothermal is nRT log VB over V sub A All right. And because we know the volume is 5 times at B relative to at A, nRT, here we go. nRT, actually, you can now do anything you like. You can put back n equal to 3, put the numbers R in there, put the temperature that you have already calculated in there, or you can say once again that actually บอกอาจารย์ nRT is also PV. So up to you, because PV is always equal to nRT. Okay, so you can go back and then you can use P times V, and that will give you nRT exactly the same. Okay, so up to you now. Everything should be okay. And this will give you 5. So that is 5. P times V. It could be PAVA, or it could be PVBV, VB. Okay, here we go. And that's it. So the answer will be just plug in the numbers and they should be okay. Oh, punch calculator, log 5. Yeah, LN5. Just do the calculator, just punch in the numbers. Yeah. But actually, if you leave it there like log 5, it should be fine too. Yeah, it shouldn't be a problem. อาจารย์ธเนศไม่น่าว่าอะไรนะ คือเป็นอาจารย์เองอาจารย์ก็ทิ้งล็อกไฟล์ไปเหมือนกันนะแต่ว่าไปแล้วนะมันไม่ได้เรื่องใหญ่เนาะแค่ผมขี้เกียจกดเครื่องนิดหน่อยอาจารย์ช่วยกดให้หน่อย Alright, but anyway, this like meets halfway, so you just try to do as much as you want up to a point that it seems alright. ไม่งั้นเดี๋ยวอาจารย์ต้องไปกดเครื่องเองทั้งหมดก็จะดูอะไรอยู่อะไรเงี้ย But I think log 5 is okay, but I think it's not a big of a deal if you just punch in the calculator for the log 5. So okay. All right, part D calculates the net work done by the gas after one complete cycle. Okay, one complete cycle. So the only thing left for you to calculate for this one is, because you already know what is going on coming from A to B, right? Now you going back from B to C, you will get the area under the curve that looks like a rectangle here, but it's going to be negative work. Yeah, because you just subtract that out. And we all know every time you have a cyclic process, the work done per cycle is just the area enclosed by the path itself. Okay, so that's why you take the area that you got from part C, subtract out that green area, then you get the work done for each cycle. Okay, so that should be good. So part D, you just calculate the W from B back to C, B to C here, and that's going to be 1 atm. Let me write just a number now, and then you go final volume, subtract initial volume 50 liter. So of course the numbers will take care of itself. You're going to get negative work done because you say final volume, subtract out the initial volume, you're going to get negative. So that will be negative. Now you can do that unit conversion, turn everything into Pascal and cubic meter, 40 times 10 to the negative 3 cubic meter. Here we go. All right, and once you have that, then you say the net. Let me use rate here. Net W is going to be the W from A to B plus W from B to C plus WC back to A. But of course, C back to A is 0 because it's a vertical line. There's no work done there. So that will be part C. Subtract out that green number right here and just put it in the box here. And that's it. Done. Okay, very good. Yes. Okay. Let's move on. So that's for the work parts. Get going. Part D, part E. What is the efficiency of this engine? All right, so we know efficiency, you can calculate from W over Q hot. So that's a part that you have to sort of draw in the heat. So actually the W you already calculated. This one is done. Okay, that's from part D. So the only thing left for you to calculate is what is the Q hot. Okay, all right, so you go back here. And this is going to be, I think it depends on your approach now. Over here, you can look at this one. Going from A to B is an isothermal process, right? Okay, so isothermal process, delta U is 0. Okay, yeah, so that means Q equal to W. All right, okay, so you already calculated W for A to B. So that means that numbers will be exactly the same as the Q. Okay, so in this case, I can say that it's a Q in, QAB. Okay, all right, that's one part. Now, you can move on to B to C if you want. But from that, well, we can get away by not doing that if you don't want. But the trick is this one will give heat out, B to C. Okay, because we know from experiences, I think you have done this many times, when you have isobaric process, when you compress the gas, the heat will flow out from the system. Okay, and that will be the part that actually the one that we call it the Q cold, right? Because that's the part that you discard heat out. So let's say, hey, because it's an isobaric process, don't calculate that one. Let's go back to the easy one. From C back to A is a constant volume process. That one is easy because from C to A, W from C to A is 0. Okay, that make it nice in the sense that the heat from C to A is going to be the same as a delta U. Yeah. All right, and that make it a lot easier because it's going to be 3/2 NR T final minus T initial. Okay, but then we use the equation of state one more time. nRT equal to P times V. So that means I can do 3/2 nRT at A is going to be PAVA. nRT at C is going to be PCVC, something like this. Yeah, and you can read out the pressure, you can read out the volume, everything is already there. But we know at the end, whatever is going on here is going to be positive heat. That means heat also flow in. So I can write an arrow here as well. Here, there will be heat QCA. So I hope this clear up everything. So in this cycle, going from A to B, heat flow in. B to C, heat flow out. C back to A, heat flow in. So what should be your Q hot? So it's going to be QCA plus QAB. You guys with me? Because that's the one that you draw in the heat into your system. Okay, and that's it. So you use these two numbers that you got from your calculation, and then you can now plug in here. So that will be equal to W that you already got from part D divided by QAB plus QBC. Done. Something like that. Okay, now? All right. So very good. And now part F, calculate the efficiency of Carnot engine operated between TA and TC, where TA is the temperature of gas at point of failure. Okay. Oh, okay, this is good. All right, so part F, that's the one that we discussed. The formula is given a little bit. So you can turn that W over Q hot into Q hot. Okay, let me put absolute sign just to be clear. So we don't have to worry about the sign anymore. Minus Q cold over Q hot. So this one just quick review what we got before. So this is just the efficiency of any heat engine. Yeah. And then we can turn this into Carnot. by use the ratio between the heat in and out, Q cold and Q hot. So that will be in form of TC over T hot. That's according to the Carnot relationship. Okay, okay, all right. And that's it. So all you need is just take the ratio between two temperature, the temperature at point A or B divided by the temperature at point C. Okay. Actually, you already know what the temperature at point A or B, but you don't know what the temperature at point C. But that's okay. One more time. Okay, let me write like this. It's going to be T at A over T at C. Yeah, this is what we talked about. However, this ratio can be calculated once again from PA, VA, over CA, PV, on and on, right? So what I can do is I can pair this with PAVA over TA equal to PV of C, sorry. PCVC over TC. If you want, this is one way of doing it. You can find the ratio between two temperatures by refer back to the information about the pressure and volume. That's one way of doing it. Or you can calculate temperature at C directly if you want to, because all of the information is already here. So if you're focusing on what is going on at point C, okay, here, let me drag it out here. At C, PCVC equal to nRTC. You can calculate like a net temperature at point C if you want. And then you take the ratio later. It's up to you. Okay, because right now we are flooded with information everywhere. So you can use any way you like. So you can do TC equal to PCVC over nR. It will be the same thing. And then you take the ratio between two temperatures later. Okay, let's do it. So, but I mean, personally, I would go like this because it's just taking the ratio. It seems easier. I don't have to do that number of mole multiplied by the R on and on. It seems to be crazy. So I can do TA over TC is going to be PAVA over PCVC. But we already know the ratio between these is going to be lying around number 5, right? Because you expand 5 times, you compress it 5 times, it's going to go up and down like this. So A and C are connected through iso volume matrix. It's a constant volume process. Okay, so they're having the same volume. So that means I can cancel these two. So the ratio between two temperature is going to be the same ratio of the pressure. Okay, with me, guys? Okay. So in this case, when you come back to this curve over here, you see that the pressure is up 5 times from C to A. So that means the temperature will up 5 times as well from C to A. Okay, so that means the ratio is going to be 5 or 1 over 5 if you want. So in this case, it's going to be 5. Yeah. Okay, here we go. All right. So I think I got this one opposite, sorry. T at C over T at A. Here we go. All right, so once I get that ratio between the temperature at lower temperature and higher temperature, C and A, I just plug it back in here. In here. So that's what I get, 1 minus 1 over 5. So that's 80% if you want. Okay, let me put 0.8 for now. 0.8 or 80%. Okay, here we go. So that means if you can replace your engine with the Carnot engine between these two temperatures, then you can achieve the possibility of 80% efficiency engine if you have that sort of machine with you. Okay, no? Okay, all right. So I think this is a very good example, actually, because I think as you have already seen, you have only 3 parameters to talk about. It's either the Q, the W, and the delta U. So it's going around here. And because we're talking mainly about gas, so you combine that with the PV equal to nRT. That's pretty much it. แต่อาจารย์เข้าใจจริงอันนี้ก็เป็นหัวข้อที่อาจารย์รำคาญอะตัวเลขมันเยอะ it's annoying like pressure here volume there temperature here you know compare here expand compress it's like need a lot of paper space ต้องทดเลขเยอะหน่อย all right but everything seems to be doable I think problem 6นะอันนี้เลยใช่ไหม oh sorry 6 oh no right this is optics so according to อาจารย์ธเนศ I think we have 1 week less than last trimester so that's why last trimester we like study another lecture before midterm so that's why there is an extra topics of optics coming in but this one it seems like we short by 1 week so that's why we sort of stop everything at sounds yeah แต่อาจารย์เดาว่าอาจารย์ธเนศนับจำนวนสัปดาห์ผิดอาจารย์คิดว่า อาจารย์คิดว่าจำนวนวีคมันเท่าเดิมอาจารย์คิดว่าเพราะเนี่ยวันนี้เรานั่งชิลมากเลย ใช่ป่ะเพราะธรรมดาเราสามารถเรียนได้อีกเรื่องหนึ่งอ่ะหมายว่าถ้าจำเป็นนะหมายถึงว่า actually we can study one more lecture but it's like okay that's good for us because exam is tomorrow it wouldn't be nice to study anything anymore today so พออาจารย์ธเนศบอกเราช็อตไป 1 week บอกโอเค agree okay let's cut it short that's good ไม่งั้นไม่ไหวรัชเกินไปก็ไม่ดีนะครับ Okay, but I think overall you guys should be fine because the exam will be pretty close to the past exam. So you see the level of the question that will show up. Okay, and I think the rest is just make sure that you do everything step by step. Okay, it's not complicated. It's not like super hard questions. It's just like straightforward questions. So just make sure that you don't make any mistakes. I think you should be fine. ไม่น่าเคิร์ฟนะอาจารย์คิดว่านะ because I think we just gonna go according to MUIC like that is like what above 90 is A below 60 is F I think we just gonna go along with that like scheme yeah so you compete with yourself yeah, don't blame อาจารย์ don't blame your friends or whatever it's like okay it's purely depending on you Oh, it seems like no questions from Zoom session. Okay, very good.
problem 7
ครับผม
ที่ทำอะไร
problem 7ไหนครับ past exam ป่ะ
ใช่
โอเค problem 7 6 7 okay, let's see. Person stands 2.5 meter directly in front of a speaker as shown. Okay, so I think that's the black dot there. There is another speaker 3 meter away from the first. Okay, both speakers play the same frequency, so everything is in phase. Very good. Assume that the speed of sound is given. What should be the sound frequency if the person observes a constructive interference between two sound waves from the speaker?
อ๋อโอเคอาจารย์ไม่เป็นไรแล้วครับ
Okay. อะไรวะ What was that? Okay, but we have อันนี้คำถามมีแค่นี้เหรอ
ใช่ครับตอนแรกผมงงคำถามอยู่ครับ
เฮ้ย ข้อ A นี่ตอบอะไรวะ So what's the question? What's the answer? What should be the sound frequency โหตั้ง10 แต้มเนี่ยโอ้โหมันคะแนนมันเยอะจังวะเนี่ย What should be the sound frequency? Oh, okay. This is kind of, it's not tricky questions, but it's like testing your confidence a little bit. Oh, interesting. So the answer for part A is actually the same frequency. It's not going to change anything, right? Think about it. If I have two speakers, I'm playing, let's say like 500 hertz sound, you're going to hear 500 hertz sound. There's no way else that I can hear, right? There's only single frequency coming out. But the only thing that is going to change is either you're going to hear the sounds like quiet down, or it's going to be like louder than normal from one speaker. But in terms of the frequency that you're hearing, it's going to be the same frequency. So part A, whatever frequency that's coming out, that's going to be the same frequency that you're going to hear. Okay. Doesn't give you anything at all.
บอกว่าเป็นเพียง frequency เลย
นั่นน่ะดิ Observe constant. What should be the sound? What should be ด้วยนะ ไม่ใช่ what is the sound frequency เลย I think information is kind of, is that missing or what? Okay, but anyway, we can test. Okay, so I think this is a good exercise to practice the interference that we just sort of discussed. So the key point is this: you just measure the distance from two sources. Here we go. All right, we can call it, we use R though, right? So we can call it R1 and R2. Okay, all right. And because the number is it a good number? No. 3 กับ 2.5 โอเค you can do Pythagorean a little bit โอ้ทำไมมันไม่ให้แบบ 3 4 5 อะไรอย่างเงี้ยนะ okay, something like that. Okay, anyway, so it's going to be square root 3 square plus 2.5 square. All right, anyway, and then you do R2 minus R1, and the key is because it says it's a constructive interference. So that means these numbers that you're getting has to be multiple of lambda. You guys with me? Okay, now. All right. So that means, of course, n can start from 0, but of course, this is not going to be the 0 case, because in the case of 0, it means you have to be at midway exactly, right? When n equal to 0 means you are at the same position between two sources. R1 and R2 must subtract out to 0. So definitely there's not going to be 0 for us, but it's going to be, it could be 1, 2, 3, on and on. Okay, so from that information, it means there will be a possibility of many wavelengths that can match this given information. Okay. And then I can sort of call those lambda to be lambda 1, lambda 2, on and on. And then you can use those lambdas to calculate what should be the frequency by taking the velocity of sound and divided by the lambda that you just get, lambda 1, lambda 2, lambda 3. So it could be on and on. So there are multiple of frequency that's possible for this given information. Okay. คราวนี้อาจารย์เลยคิดว่าไม่แน่ใจ what does it mean by what should be the sound frequency and the answer is in hertz อาจารย์ว่าเหมือน information มันหายไปนิดหน่อยนะ There is another speaker which is 3 meters away. Interesting. I don't know. เบิร์นข้อนี้อาจารย์ก็ไม่ได้ตรวจซะด้วยเทอมที่แล้วอาจารย์ธเนศเป็นคนตรวจเอง but that's kind of interesting. There are so many possibilities here. Both speakers play the same frequency. Assume the speed of sound. Okay, let's say if the information given is just this, then there are so many possibilities here. All right, but at least let's say that's the principle of how to calculate then. Because if to make it a little bit precise, maybe it can be like what should be the lowest sound frequency possible or something like this. And then you pick like n equal to 1, something like that. Then that will give you like a specific frequency that's possible, something like that. Maybe I'm guessing it could be something like that. All right, part B. A person now starts to walk to the right. What distance does the person need to walk from the initial position to observe the minimum sound? Okay, so this might make sense a bit. This one is easy to do because now when you start walking, eventually you're going to meet the destructive interference point. Okay, so you assume that there will be another point, maybe here, that now you have to recalculate again. Let's say that's X. So you're walking away from the original point by a distance of X. And then the new distance will be, okay, let me call this R2 prime minus R1 prime. Yeah, that's a sort of new point. The R2 will get longer. R1, of course, will get longer. So this is going to be, this R1 prime is going to be equal to R1 plus X. You guys with me, yeah? Because you already walk out another distance of X. And then R2 prime, this is going to look pretty bad. It's going to be 3 square plus R1 plus X square under square root. Okay, here we go. All right. But then if you get this, all right, so let me write it as, I just keep it as R2 prime minus R1 prime. What should you equate this one to? What do you think? So that's why I'm saying that I think maybe there's a missing word in part A. Because let's say if part A, I say that's the lowest frequency, right? So let's say you pick n equal to 1. Then when you walk away from the original point by another distance X, you hear the quiet point. That means if that n equal to 1, that's 1 lambda, right? So when you walk away from it, it's supposed to be what? It's supposed to be 1.5 lambda. You guys with me? งงไหมไม่งงเนาะ Because that's usually what happens. You starting from like, if you already like 1 lambda, when you walk away from it, then you're gonna hear the quiet part of it. So that means you already move away by another half of the wavelength. And if you keep walking, you will hear the loud sound again, and that will be 2 lambda. And then if you keep walking, it will be 2.5 lambda. You hear quiet sound. They hear nothing again. And they keep walking, you hear 3 lambda, 3.5, 4, 4.5, 5, on and on. So you hear the alteration between quiet, quiet, loud, quiet, loud, quiet, loud. So given that if we agree that the part A is n equal to 1, then this will be 1.5 lambda. So something like this, all right? Or just to be sort of general, it's just n plus 0.5 lambda. Okay. All right, good luck in exam. All right, so all you need to do is just add additional half the wavelength into whatever you calculate from part A. And that's what's the condition that you need for part B. Okay, all right, so that's the whole concept here. Very good. But seems like the number for this one is bad. Really bad. เอาเหรอ อ๋อ okay, okay. อันนั้น really bad, eh? Okay, okay. All right. Soอันนี้ so I wish it's just like 3, 4, 5 or I don't know. Okay, but this is, if it's not too bad, then it's not too bad. Okay, all right. But I think this is a good exercise again, just to confirm what does it mean by interference. Okay, good. Very nice.ครับผมแต่ว่าน่าจะเฉลี่ยเท่ากันหมดเลยนะคือหมายว่ามัน like I think the final includes all the topics I think that we study, like starting from the first topics that we sort of study and then sort of go through. I think the only thing that's missing is the one that we didn't study, the standing wave. That's the one that I say like, oh wow, that's missing. So we didn't discuss that. The last part of the last portion of the handout, number 5, yeah, that's the only thing that's not in the exam. But everything else, I think they're all on there. Oh, there's one part you guys don't have to worry about it. That is the linear wave equation. Remember the one that we have to differentiate like crazy, like do it twice in x, twice in time. That's definitely not on. Yeah, don't worry about that one. So just so you know, that one is just like FYI. Just like, hey, you have seen second order partial derivative once. Yeah, so at least you can sort of familiar with it a little bit more than supposed to be without it. Okay. So I think overall seems all right. Yeah, okay, no lenses. Yeah, Doppler effects, oscillations, heat conductions there.
อาจารย์ครับถ้าเกิดเขาถามว่ามันเป็น simple harmonic ใช่ไหมแล้วถ้าเกิดในโจทย์มันเขียนว่ามี oscillation อยู่เราสามารถประจุได้ว่ามันเป็น simple harmonic.
Yeah, every time you hear the word oscillation in our course, at least you can assume simple harmonic right away. Yes, yes. So the key point of the simple harmonic is you have one single definite frequency. That's why we say simple, because you have like pure frequency to talk about. So that's simple harmonic. Yeah, the sound of your voice and everything is not simple because you have combination of frequency coming out from vocal cord and everything. So that's not simple. But when you have a single frequency, you can assume simple harmonic. Make it simple. Okay. Okay. Intensity, waves equation, thermodynamics, of course, specific heats, expansion. Okay, so I think that's cover all the topics that we studied.